All right, so it's one more, but there's 6 points here we have to actually simplify with. So we're going to use this logistic model here, and it's scenarios about the population of a fish farm in T years. And so it's modeled by this logistic model of 1,000 divided by 1 plus 9 e to the negative 0.6t. And so first thing they want us to do is graph the function. Okay, well, we know how to do that. We plug that in our calculator and it'll do it nicely for us. We don't have to do too much. And so that's from our last one. So this is going to be 1,000 divided by this quantity 1 plus 9e to the negative 0.6x, arrow down, parenthesis, and all right, so what we have to do now is we have to turn off some stuff. So when you're doing this, you're going to have to remember what you're doing and how it works. So now our window, um, let's go now and see what it has. So it looks like we need to maybe go further. Let's go maybe negative 20 to 20, and we can go by 5. Maybe let's go up to, I don't know, 1200, and we'll go up by 100. All right, so now that's going to give us our model. So that's what our logistic model looks like, and our C here is at 1,000, okay? So that's good. So we've graphed the function. Now it says, what is the initial population of fish? Well, our initial population is going to be at time equals 0. So guess what? We just hit trace and it says x equals 0 and the population is 100. All right, so we have that one right away. So what is the initial population of fish? It is 100. Now, is there another way to find it? Sure, there is. So what we can do is we can say, well, P of 0 is equal to 1,000 divided by 1 plus 9 e to the minus 0.6 times 0. And so, well, e to the 0 is going to be 1. And so that's going to be 1,000 divided by 1 plus 9 times 1, which is 1 plus 9, which is 10. And so that gives us 100. So we got it from the calculator directly, and we also calculated it by plugging in the t equals 0. All right, so the next question. To the nearest tenth, so the point decimal, one decimal, what is the doubling time for the fish population? All right, well, what do we have? Okay, here we have to remember t is equal to ln of 2 over k. This is the thing we need to have for doubling time. Now, what do we know? Well, we have to find what k is first. Well, k, that is going to be coming out of this. And so we're going to have to say, okay, well, that's going to be equal to minus ln of the 0.6. Okay. Now, do we actually need to calculate it here? Now, let's just plug it in here, and then we can calculate what that is once we plug it in there. And so that's going to be ln of 2 over negative ln 0.6. And so if we plug that into our calculator, let's clear that. So we have ln of 2 divided by negative ln of 0.6. We get 1.35, and it said to the nearest 10th, so that was going to be 1.4. And this is going to be in years. So that's how long it's going to take to double our fish population. All right. So what's the next one? It says, to the nearest whole number, what will the fish population be after 2 years? Well, that's going to be pretty easy. 20. That's going to be what is P of 2. Well, again, we have two ways to go on about this. We can plug it in here and get our value, or we can go ahead and plug it in our graph. Now, hopefully, I don't know if we actually still have it. We don't have it anymore. All right, so what we can do is we can go to our graph and we can say, let's trace and find out what 2 is. 269.48. Now, we're not going to want to round down on this one. We'll round up to the nearest fish because we've already got 269, so we'll round up to the nearest fish. So we'll call that 270 fish. And the other way we could do this is we could say 1,000 divided by 1 plus 9 e to the negative zero point 0.6 times 2, arrow down in parentheses, and we get the same thing, 269.487. And so either way we've done it, we're going to get, that was 269.48 or approximately 270 fish. Okay. So that was not too bad. All right, what about 21? To the nearest tenth, how long will it take for the population to reach 900? Okay, well, this one we can't just plug it in our calculator and do it very easily because, we can try to get close to that value for the y value. But what we really need to do is we're going to say 900, that's the population we want to get to, equals 1,000 divided by 1 plus 9 e to the minus 0.6 times t, and we want to solve for that t. Okay. Now, if we do this, we could take and multiply both sides by this value and divide by the 900. And if we do that, basically those two things swap. And so when we do that swap, what we get is 1 plus 9e to the minus 0.6t equals 1,000 divided by 900. Okay. Now we need to solve for t, so we'll subtract 1, and we'll subtract 1, and 9e to the minus 0.6t equals, now if we take the 1,000 and divide that by the 900 and then subtract 1, we basically have the value of 1/9 because that's going to be what, 1, those two zeros cancel, those two zeros, 10 over 9. And if we subtract 1, 9 over 9, then we just have 1/9 left. Okay, so that's how that's going to be, because this is going to be 10 ninths minus 9 ninths, and that's 1/9. Okay. Now to get rid of this, we're going to have to divide by 9 or multiply by 1/9. So if we do multiply by 1/9, we'll have e to the minus 0.6t equals 1 over 81. And now we can take the ln of both sides, and when we do that, that comes down. And because we have 22, we might have enough room for this. We have negative 0.6t equals the ln of 1 over 81 divided by negative 0.6. And so t is equal to, now we just take the ln of 1 divided by 81 divided by, oops, where's the 1? Divided by the negative 0.6, and we get 7.32. So that should be the number of years. But it wanted it to the 10th as well, so that's going to be approximately 7.3 years. Okay. All right, so that's 21. So now 22. What is the carrying capacity for the fish population? Justify your answer using the graph of P. Well, we don't have to use a graph of P. We will, but our carrying capacity, remember, is always this C value. So for 22, C equals 1,000, so that's the carrying capacity. And if we look at our graph, that will show the same thing. So our carrying capacity, if we trace that, the further we get up, it's going up higher and higher and higher. It's getting closer and closer to that 1,000. And, if we took our window out further, take it out to maybe 50, maybe by tens, then we can say, okay, as we keep going out, it keeps coming closer and closer and closer to 1,000. And like I said, once we get to a certain place, we're going to run out of decimal places, and then it's going to say it's 1,000. but that's not really true. We just have gotten past, you know, 5 decimal places. It's probably still a bunch of variables after that as far as the numbers go, but it shows 1,000. So our carrying capacity is that limit up there. And so that is why we say C is 1,000, because that's our carrying capacity. And so either way we look at it, that upper bound, that horizontal asymptote at C equals 1,000 is our carrying capacity for the fish population. All right, so that's all I have. So hopefully that will help you with this section.